Well, friends, today we're talking about Math 105, Section 4.5, and we're dealing with the number e and something called continuous compounding. And the reason that these two things are intimately acquainted with one another is if I have a yearly rate of r, and I express that in as a growth factor, we know that b is equal to 1 plus r. And that's if I compound, if I collect interest once a year. If I then look a yearly rate of r, but I'm going to go at it twice a year, b will be equal to 1 plus r over 2. But if I'm going to look at this thing yearly, just for this to make sense, I'll really have 1 plus r over 2 quantity squared. If I was going to do this again, but look at something like weekly, I would have this b is equal to 1 plus r over 52, because there are 52 weeks in a year. And if I went for a whole year, I would have to raise that to the 52nd power. And it turns out if I keep going, let's say I go 1,000 times a year, we'll have our growth factor of 1 plus r over 1,000. And so to get 1 year out of it, I'll have to do 1 plus r over 1,000 raised to the 1,000th power. And what happens, we're beginning to stabilize what we stabilize to. If I take this 1 plus r over n raised to the n, and I say, okay, so n is the number of compounds I'm going to do a year, and if n goes to infinity, then this terrible thing goes to e to the r. Okay, so this is why we call it continuous compounding, because I'm compounding faster than once a second, faster than once a millisecond, faster than once a nanosecond. We are just compounding super duper quickly, and we get this e to the r. Now, I'm not usually going to use r. What we'll have is we'll have y is equal to p naught e to the kt, where p naught is our initial investment, k is our continuous continuous rate, and that's going to be expressed as a decimal, and t is the number of years, or how often we're going to be compounding. So, for example here, if I said that a population grows continuously at 7% each year and starts at, say, 2,000, y will be equal to 2,000 e to the 0.07 t. Let's just put these things out there so the p naught value is our initial investment, 2,000, yeah? That our continuous growth rate is 7%. And, I can think about this. I can say this is e to the 0.07 raised to the t, and that shows us that our growth factor, b, is equal to e to the 0.07. And I think that right there is not that great of a stretch of the imagination. We just used our properties of exponents to break that thing up and to get our specific b value. Now, if I was going to throw this into my adding machine, and I will, we have an e button right here. I can say second e raised to the 0.07 just to see how big of a growth factor is. And this is 1.0725, blah, blah, blah. And so what does that tell me? That when I'm growing at 7% continuously, grows faster than 7% per time or annually. And this will be true of all things. If I have e to the any number, it's going to be greater than 1 plus that number, because the continuous growth is a faster growth than an annual problem. The one thing I can say here is that if something is decaying continuously, say we have a population start at 300 and decay continuously by 3.2%, we'll say each month, y will be equal to 300, no great stretch of the imagination there. Because we had continuously, we're going to have e as a part of our growth factor. But because it's decaying, negative 0.032. And then, I could write it like this, all of that raised to the t, but I don't. I use my properties of exponents because I'm a master, and I have 300 e to the negative 0.032 times t, and we're out. Let's continue thinking about these things, and maybe we will have something like this. A population grows by 15% annually, yearly, and a different population grows by 14% continuously. Which grows faster? Well, the way to approach this is to compare the two different growth factors. The growth factor for my first population is 1.15. That's a 15% growth every year. For the other population, b is equal to e to the 0.14. And while, I can see that I have something here, once again, I'm going to have to reach to my calculator to figure out exactly what this value is, or some approximation for it. 0.14, and I get 1.15027. So it turns out that 14% continuous growth is greater than 15% annual growth, and that second population is the champion. Let's do one last example, and how about a population decays by 13%, and in year 2, there were 2,700 people. So what we can do is, we can certainly set up that y is equal to a e to the negative 0.13 t. And I know that many of you are solving for a by plugging 2 in for t, by plugging 2,700 in for y, times 2, and you're solving, yes? You're going to solve for a, and a will equal 2,700 over e to the negative 0.26. And sure, I could resolve that more, but we would have a formula and we would be done. I don't like to think of things that way. I prefer to say, okay, I have this declining population, and in year 2, there were 2,700 people. And so what I'm going to do is I'm going to make this equation right here using this 2,700 like a fake a value. Y is equal to 2,700 e to the negative 0.13 t. That would be this dashed equation right there, but that's not the one I want. I need to take this and then shift it to the right 2 units. And so to do that, I'm going to have a t minus 2 in my exponent. So as much as I love being able to solve for your initial value, I think being able to use a point in space is a much faster way to attack. And if I wanted to know what that initial value was here, I could always put a 0 in, and we would have, I could say y evaluated at t equals 0 would be 2,700 e to the negative 0.13 times negative 2, which is exactly the same thing that you got for A. But here I'm telling a story that says in the second year, there were 2,700 people.